Maybe.
Okay, I'll let you full screen the thing. Yeah, I don't know how to full screen it. I don't use PowerPoint so much. Perfect.
I shall go around. One goes out. Halloween must have taken some of us. The witches.
Somebody say start, I will start.
Start.
All right. So I put together a couple of thoughts about going from proton to nuclear, GPDs, MPDFs, at an EIC, and RHIC, and some couple of thoughts on the Wigner function too. So bear with me. I'll start actually talking about EPs just to set the stage. I gave already some detailed talk on week 1, another review on week 4. So if you want more details, go on YouTube and check me out. But I just talk a little bit about DVCS and DMVMP in Proton, because basically talking with some general concepts in Proton and in nuclear are the same, and so we had studies already done in this area, and we actually now have to think about moving to the nuclei, which is the next that I want to cover today. And I will, after the discussion that had been taking place in the previous days, I decided also to add some little background on what Pia showed 2 days ago on the experimental side of the nuclear PDFs, then nuclear GPDs, how to access also gluon GPDs in EUPC, in proton and nuclei at RHIC, and then I will talk a little bit about the Wigner in the end. So, no introduction for you in this audience, just to remind about the processes we are interested in here. They are exclusive diffractive processes. So we want to produce vector particles like a real photon in the DVCS or a vector mesons or a scalar mesons if you want. So the DVCS is usually what we consider as the golden probe. It entered white paper. It's always considered the best way to access the GPDs. And it has a meaning because actually it is very, experimental side is very clean to measure. And we don't have complications in the calculation coming from the vector meson wave function uncertainty. And also the Q-square is totally free to vary from like 1 to GV up to high Q-square. So we can actually use this as a hard scale to prove via both the quarks and the gluons. But we have always to keep reminding ourselves of the importance of vector mesons too in the accessing GPDs. For instance, vector mesons are powerful tools, either if you want to achieve a completely flavor-separated GPDs, or you want to access gluons with precision. For heavy mesons like JXI and Upsilon, one can probe directly the gluons. This is a process that is generated in a quantum gluon fusion. And so it constrains very well the gluon GPDs. If we measure lighter vector mesons, with a set of combination of methods, and I come back to this later, one can disentangle the quarks, flavor for U, for B, even for S. An alternative way to disentangle U and B, at least, is to measure DVCS on both proton and a neutron. On a collider, we don't collide neutrons, so we collide deuteron, for instance, or helium, so light nuclei. And then we have to disentangle what is the contribution from the neutron and compare with the proton. Okay, this is just to give some introductory thoughts. What are the observables that we are interested in? Certainly, the powerful one is usually considered the differential cross-section as a function of the photometric T, which is actually, it gives you already a very good access sensitivity to the GPD-H. It only weakly depends on GPD-E. So this cross-section is actually giving you sensitivity to the imaginary part of the scattering amplitude. Now, if you have a nice detector that allows a full coverage in azimuthal angle and you measure the phi between the scattering, the production and the scattering planes, so you can measure asymmetries. And one asymmetry, the charge asymmetry, actually gives you a nice access to the real part of the complex amplitude. This requires, to have a beam charge asymmetry, requires to accelerate both electrons and positrons. So this was done at HERA. It was actually earlier considered at the EIC too. So we can actually think about this and consider maybe as a possible upgrade, because there was a huge discussion actually on week 1, and it looks that the real part of the imaginary amplitude is the key to constrain the B term, which actually now is very exciting topic in this field because it gives you a connection to gravity and so on. So let's keep in mind this. Another very good probe that we actually are unique at EIC compared to HERA is that the capability that we can polarize transversely the proton beam, the hadron beam, and access actually the GPDE with more precision than just the cross-section alone. And this is through the transverse target spin asymmetry. So this is actually a nice measurement if we can make it, because opens a window to the spin physics. It gives you information on how much the contribution to the proton spin comes from the total orbital angular momentum through the G-SUM route. Few considerations also having in mind the discussion again at week 1 about the phase space that an EIC can access compared to HERA. Again, here we are talking about DVCS on a free proton. Actually, if you already see at this, look at this picture from the white paper, and this can be actually further now updated at RHIC if we want, because we are thinking of going even at lower energy. Basically, we extend this coverage from where the fixed target experiments sit down to the HERA data. These are the HERA points for the DVCS. Now, there was a discussion actually on the importance of overlapping to the JLab 12. In my opinion, this area will be precisely explored by JLab 12 in a way that we can't compete with an EIC. But there's still some importance on it. So the importance is, in my opinion, as a sanity check for the EIC itself. So we can compare ourselves here to a strong benchmark, very precise, and we can understand, at least at the first years of physics, what actually we are doing and how we are extracting things. It is actually, in my opinion, much more important physics-wise, let's say, as an impact, to overlap with the HERA data. Most of these data are actually total cross-section, the white points. The differential cross-sections, the ones that are sensitive to the GPD, H are a few points, very limited in statistics, and there is only one charge asymmetry at this point. So here the impact on current knowledge is enormous out of the EIC. What actually will pose the ultimate challenge to the theory is a fine beaming here in this intermediate region. So EIC aims to do a fine beaming square in X and T on this region. And right now, the models that usually fits to the data are actually tuned to describe the low X or the large X. And the evolution is sometimes done through rigid parameterization. So we need to challenge those models to describe the full phase space of DVCS plus the vector mesons in a DGLAP next to this order accuracy. So this will be a tremendous challenge from the precision of the EIC data, which will be great. Okay, so back to the white paper and what we did. When it was published in this paper back in time into 2013, we did a full-fledged analysis of DVCS and its main source of background, the beta Heitler, which actually interferes at the amplitude level. So we did a signal extraction the same as it was done at HERA, the same cuts to suppress the background in the cross-section measurements. We evaluated the radiative correction. We smeared according to the acceptance of the detector and resolutions. And we consider 5% systematics. That now it's our benchmark goal. Actually, HERA was closer to 7%. So it's a reasonable goal. And we did this study using a Monte Carlo which was based on the GPDs already and simulates the VCS event and was used by the H1 collaboration. So it's trained to the HERA data. You can see the usual two canonical example of energies in the white paper, which are lower the time 45 GP and 140 GV. And you can see that actually you fill of statistics all these tiny things that we consider. These are not considered randomly. It's according to the resolution, 3 times the resolution that we can achieve in the detector.
Why do you have Y 0.8 here?
It's the limit to where we are confident to do a DVCS measure. So basically, and you have seen all this, this is what came out and it's in the white paper. Again, the luminosity that we benchmark is at that time 10 inverse pentagon. So out of this luminosity, everything that we measure on DVCS in some tiny bins in Q square and X is systematics dominated. This includes the 5% systematics. If you do the Fourier transform, you already have an idea of the Bartonic densities. And so kind of the precision to which you can do the imaging. We did also the IoT, which is a very nice measurement. These are the tiny error bars, always around 0 because we didn't have the prediction in our Monte Carlo, but it gives you the idea of the precision that the EIC can reach. And everything was done, put together in a global fit with Kressel Kumeric and Dieter Müller that used their model to fit everything with the data and the data alone and the data with EIC, which is in orange. You already can see here that an EIC, after EIC is included, the GPDH for the C port will be much more constrained. Here is like a factor of 5 improvements at low T. And remarkably, we can do a first precise extraction of GPDE for the C ports. And we can constrain the blue on GPDH. We didn't have sensitivity with that model with DVCS alone to the blue on GPDE. Keep and bear this in mind. We Fourier transform, and you have these profiles that actually in 2 coordinates will come to give you the nice tomographic images that you do. And this is where the physics in the white paper ends, basically. And this is where we now go back to the board and see what is missing. So what is missing here is basically the whole set of mesons. We didn't include JPSI, for instance, in our fits. Though it was simulated, it appears in the white paper, but it wasn't included because no models at that time, and still nowadays it's challenging, can describe the JPSI together with the VCS and next to the decoder and to the fits. So this is one challenge, and I believe that once this is done, this, for example, will shrink much further, the uncertainty. We need to put the light mesons to do the flavor separation. So we will not talk anymore about C ports, we will talk about U, D, S, and so on. So there is time. So
Can you go back? Now you will have some limited range in T measurements, right? So
yes.
Yeah, so when you do the Fourier transform, that will translate into uncertainty.
Yes, I have some in the backup, and I gave actually a full talk about this and how this varies when you have a different T coverage. Now, this coverage that we have here is impressively good. So here we assume that the Roman pots will cover between 0.05 0.01 in T and 0.02 and 1.3, 1.4, 1.5. If you have this coverage, this is what you actually get. If you have a different coverage in T, things they start to be less nice than you get here. I have something in the backup, so if you want, you can look. Yeah. So that's the study that we did for the coverage of T. So this is what actually creates the figures in the white paper. So we actually assume between 0.03 and 1.6, and here also we assume 100% acceptance. And if you limit the coverage at low PT range, this is what happens. You resolve the whole spectrum of the Fourier transform and certainty. And if you lose capability of covering the large T, you actually have less precision at low impact parameter, which is where, for example, you have a nice impact on the GPDs for the sigmoids. So it's
you
really
have to also
important.
do something beyond 1.6, right? So you have some spread beyond, let's say on the upper figure. Is that, you transform?
Yeah, it's between point here you cannot see, but then with zoom in the white paper it's shown that you can do a nice job up to.
I mean, when you have T which ends at say 1.4, okay, and
Yes.
then you have to assume essentially you don't know anything, so that would blow up your.
That's right. Yes.
So that, I mean, you have to parameterize it somehow.
Yes.
So what do
Yes.
you do with that?
We do an extrapolation. What it's like. This was a code maybe written by Marco, and I don't remember precisely what is assumed, but I think that you can basically.
I mean, what is essentially, your lower plot illustrates that, right? I mean, you have two curves, and then essentially you don't know. So you have some, I don't know, power law and maybe an exponential or something.
Yeah, this is considered an exponential.
That is spreading you, so you don't know anything. Let's say up to, I mean, you have this spread which starts 0.2. You move to 0.6, you will see. I don't know. Maybe you will have some spread at 0. I mean, I'm suspicious that the spread, a lack of spread at 0 over there, right? On this figure.
Here?
No, on the top, because you don't know anything beyond 1.4 on the left figure, right?
Yes.
So.
But this is already. I mean, you don't know anything about after 1.6 actually.
I mean, these issues were explored extensively with reconstructing nuclear charge densities and looking at the quadrature error from different kinds of extrapolations. I mean, basically, you can set 100% error that whose magnitude equals the last point out to infinity and generate something very close to this. So you can say, well, it's going to fall off in some way. But I think, yeah, it's essentially incorporated in those plots on the right. And so the bottom, certainly if it's worse, if you get, so if your upper bound is only 0.8, you see things really blow up at the origin.
Yes.
And as you extend that coverage, you get smaller error bars.
So I have a question. So you assume different PT ranges, which assume that all the plots get this or don't, right? But if they don't, can't you not just calculate T?
From the vector method.
From you have the photon, you have the income.
Yes, correct. So, of course, one can make up from the missing coverage of the Roman plots by calculating the net range, the T, out of transverse momentum conservation. So that will give you a less precise T. So that means less.
But it would.
Here you will not achieve those meanings.
It would improve the blue band, right?
Yes.
But we discussed that last week quite a bit. In ECS, when you start not detecting some of the particles, you might think that by missing mass and stuff like that, you can reconstruct that. But in the past, we've seen a lot of issues with that.
So the H1 data, for instance,
really
are
something to be careful about. It's much better to detect the risk.
But camera didn't, right?
H1 did. So the three key cross sections that H1 published are all without Roman points.
Wait,
No,
he
no,
was
but
calling-
we actually are not super in
That's
agreement.
not my point. Many experiments did it. The problem is when you have experiments that are in the same kinematics and so
One
on,
experiment.
and you have the two methods, you find out that it's actually systematics are very different and it's really problematic.
Sure, but I mean, I'm just arguing if there's nothing you can do, that is the method.
I mean, at the collider H1 did. But it's like,
I mean,
it's like
most of them is data is without detecting the proton.
then there is the
Most of
endless
all-
discussion of the systematics.
Or A data in general is without detecting the proton.
What is the main source of systematic? Like dominated source of systematic for DVCS or for that?
It's the cuts on the electron, and if you don't use the Roman path, is the proton dissociation, the ground, and stuff like this.
And you have Fazio contamination,
Yeah.
huge background.
This is relevant when you go to higher, to lower, to higher, to lower.
It's relevant everywhere.
No, it wasn't relevant.
Also, your requirement,
But it depends on you.
your requirement that the beta height would be less than 60% is artificial and unnecessary. I mean,
We don't require less than 60%. This is what we achieve after we apply those cuts, and it's necessary. Okay, that is a systematic tool. If you don't, the beta Heitler dominates your cross section, and you want to subtract it, and you subtract it with a Monte Carlo, right? Because this is at the amplitude level. That is well known to the 3-4%. So that is giving you systematics in the subtraction.
but all these
60 is not.
cross-section differences, all these interference terms are multiplied by the same form factor. So those systematics are there whether you have a large beta height or not. I mean, every single spin asymmetry is an interference between
The
beta
spin
height
asymmetry
and
is one thing, and the cross section is another. So the spin asymmetry, we don't even have to touch the beta height, right? Because you will access the interference term. The cross section, the DVCS, the sigma dt for the DVCS is where you subtract the beta height contribution.
Well, at the amplitude level, the single spin asymmetries are the beta Heitler, a piece of the beta Heitler times a piece of the DVCS.
Mhm.
So your knowledge of the beta Heitler goes into your extraction.
Yes,
So
but
if
that
you're
is
concerned about,
known to a certain 3-4% coming from the form factors. So that is okay. You don't need to reduce it to the level of 60%. It's but it shouldn't be 199%, otherwise you're system. Okay. So let me move on and talk about the methods then. And this is completely taken from the Marcus Deal PhD thesis. And I'm not aware of any update on this result. So this is how the sensitivities of different methods to different work levels. And you can see here if you add like rho plus, rho 0, omega, you can constrain USD. If you add phi, Marcus claims that constrains also S. And of course, with JPSI and Upsilon, you constrain groups. And another way is to do double tagging, and I will talk about this later on the deuteron for constraining U and D. So what we did at the time of the white paper, it wasn't including that in the fit, but it was at least simulating the JPSI. So we proved that with this canonical 10 inverse pentabarn, at lower and higher energy considerations at that time, the JPSI can be precisely measured. and here the Fourier transform gives average densities that you can consider perhaps to be already gluons, because this is what is the precise sensitive. And recently there was a study from Zenedin and collaborators from Temple that actually proved that even upsilon is actually doable at an EIC. So here they actually use 10 times more luminosity. So here we are talking about 100 inverse femtobarn, because this is a heavy meson, you need more statistics to do precise measurement. But already with 100, which is completely at the average at the EIC capabilities, we can do a very nice precise measurement. This is the phase space that we covered. Strangely, okay, compared to what we show usually in the white paper, that we show a low and a high energy, here there is an intermediate energy, basically. So it's considered 10 on 100, which corresponds to 63 GeV. And you can do a nice job. So if you want to go down an X, which is what you do constraining the gluons or want to do, basically this still holds, because you can do, okay, there is like a luminosity drop in the collider designs, but this is compensated by the fact that the cross-section is higher 3 times, over factor 3 at least, if you go to 140. So we can certainly measure all this set of vector mesons at an EIC, it's not an issue. So we did a workshop recently at Stony Brook with the Center of Frontier Nuclear Science, actually dedicated to this business. Julia was there, Christian Weiss was there, and helping running it. So here is a couple of conclusions. This was a very small community workshop, but the point here that I stress is there is a dedicated community with great interest on including now these mesons in the feeds of GPDs. And we are aiming to the next level impact studies for the EIC. So the idea that was coming from this workshop is that we can use a shared platform, the same as it's done for the PDFs by XFilter, which is called the Partons project, and it's from Harvey and Jakub in Warsaw. And this can actually allow us both to keep the knowledge going on, because right now there are 1-2 models, one from Peter, one from Fazio and Peter, and they are kind of sitting in personal laptops, and there is no way we can do the feeds. People are busy, and you know, the EIC is 10 years to come. We don't want to lose this knowledge, and we want actually to put the community more together to work on this problematics. So this is what we envision, and there will be now a follow-up in Warsaw organized by Jakub. January 22-25, where we really want to do hands-on work on running this platform.
2019.
So,
2019.
Yes, correct. 2019. So, if anyone, I know Julia is interested, if anyone wants to help us doing this and comes to the warm Warsaw in January, we appreciate it. We appreciate it. Okay? So, nuclei, this is what we are supposed to talk actually. So, nuclear modification, we always brag that we want to understand the nuclear environment, and we do it for the PDF and for the GPDs. Couple of backup on what Pia showed like 2 days, 3 days ago, 2 days ago. Okay, what we did actually that created these pictures in the paper and the feeds that Pia showed. So we actually simulated inclusive GIS with PIA, and here we assume a total of 10 inverse femtobarn and a systematic of 3%. These 3% are coming from luminosity and PLD of the electron. The luminosity itself is an overall systematic, and it's accounted to 1.4%. You have these impressive results if you have these 3 energies at an EIC, from 30 to 90, basically, in the center of mass, and you can cover all this nice region that really starts at low x, 3 × 10⁻⁴, and goes at quite large x, 0.5.
Wait, why
Yes.
is CTEC 14 error bars are so large at low x but not at high?
This is not secret.
What is
EPPS 16.
This is EPPS 16.
So because EPPS 16 only gives ratios, so to get an absolute uniqueness and
Okay.
PDF, and they use, or we use here CT4.
Yes.
So you take CT14 and multiply it with the EPPS ratios, and that gives you the nuclear PDF.
So kindly you can see that the challenge at low X is that the theory really doesn't, there is no data constraining anything. So of course the uncertainties are large. It was a comment that, the error bars are here now visible is because we put this log 10 factor to put everything in one collective plot, which is similar to what Hera usually does. But let me pick just two examples in Q square, low or high Q square. Here you can see the uncertainties, because I took that factor off of the plot. The uncertainties are very little still and really dominated by the 3% of systematics at 10 inverse 20. I will quantify about this later. And also you can see here basically the idea on how you improve on the theory knowledge. It's a more quantitative idea. So we did a ratio between the width in the points and the width in the theory. And you can see here that the width in the points and the error points are just 10% of the total width of the theory uncertainty. And even at large X, it's still 1/2. So the precision really squeezes so 1/2 the uncertainty in the theory. So it's a nice job that we can do for inclusive DIS. Now we also consider the radiative effects, and this is actually a source of discussion, how much they must be constrained, how much systematics they cost if we correct for this. So radiative effects, here you can see we use Django to simulator to generate those because they are not NVIDIA. So here you can see the spectrum, the energy spectrum of the radiated photon. You can see that it's basically below 1 GeV, and it's always collinear to the scattering electron. So the theta angle of the photon is larger than 3 radians. I don't show here the phi because it's basically flat. So you have a flat distribution in the azimuth angle. And the radiative, so
polar angle. Oh, because 3 radians because it's
the convention that you
yes, okay.
The Hera convention that we use.
Scattered. I mean, there's pre-radiation and post-radiation. So shouldn't there be 2 spikes, or this is?
Here we consider the initial state effect.
Okay. So it's collinear to the incident electron.
Yes.
You say scattered electron on this slide.
Oh, wait. So this is collinear to the.
If it's pre-radiation,
right?
I mean, because post-radiation you can detect. You can detect the photon. So it makes sense to focus on the pre-radiation as a background.
In the collider, you can detect both.
No.
You cannot detect
the initial state usually goes really collinear.
There's 5 GeV of power.
So the stuff that is produced in the beamline will come out.
But there's 5 GeV pileup of photons per crossing at 0 degrees. So you can't resolve individual photons.
It's
Yeah, it
very
would be
That's
smaller
right.
than this.
So this is why we have an issue of the road, right? So because we cannot really detect it. So we have to correct using this Monte Carlo based like unfolding where you do this correction factor, which is the ratio between this cross section at the first order and the Born level. So here what we evaluate is actually that they can become large. So they can become between -4 and 0.5, 0.4. So we have actually maybe to think about these radiative corrections at certain point in detail and what it implies for our measurement. So we did also this FL extraction. So for FL, we need to have a lever arm in Y+. So 3 center of mass energies is what we consider it. And also we consider to stop where we don't have enough lever arm to constrain the field. We consider 2 different electron energy, a lower and a higher one. If I remember correctly, it's 5 and 20. So this translates in 3 different proton energies. So this translates in 6 sets of energies: 3 for the lower electron energy and 3 for the higher electron energy. And this is what we use these 3 points to do the FL fits. Now here we consider an overall 10 inverse 10 to the 1. It means that it's the sum of these three energies that we use to be 10, not just the single one. So it's 4 plus 4 plus 2. And still, we are systematically dominated in the inclusive for 4 in this case, as an example, inverse Ventover on this energy. You can see here the ratio between the statistical uncertainty and the total uncertainty. Total statistical plus systematics in quadrature. You can see here that basically everywhere the statistical is never above 1%, few percent, fraction of percent of the total uncertainty. You have to go to very large Q-square to hit the point where the statistics will make a difference. So this is really a very high impact, I believe, year 1 physics at an EIC.
And that doesn't show what the, I mean, that error, that's the error on sigma L, or that's the error on cross-section?
On the cross-section.
Year 1.
So,
Year 1.
but FL is a fraction.
Why not?
Go running 3 different energies first.
Look, this isn't the time to talk about.
So you can just start with it. This is what you. This is for the FL maybe is not okay. Year 1, let's say the inclusive.
Yeah, that is year 1.
Yes. Now for the FL.
Certainly.
Unless you want to run 3 different energies, which is not excluded
Yeah,
by
but
any
you
law
also-
that you run 3
you
different
also want
energies.
to
Are
run-
RHIC, we modify energy like crazy.
You also want to run the protons, and at the end,
At the end, you
you
have to
should not
agree
say
with
this as a year 1.
Well, whatever you want.
Don't put words on my mouth that I
You
didn't.
just said
So-
it's really year 1.
No, I mean the inclusive for this stuff, right? Not the FL. So, all right.
But, so I still am confused by this plot. I mean, if I look at a region where the color is green, are you telling me that, so you're saying the statistical error on the extraction of FL is less than 10%?
This is cross-section.
So,
This cross-section at this energy. So the one that we show here, but even at less energy.
so it tells me nothing about how well I can measure FL.
This is not an argument. Okay, I'm sorry, maybe I shouldn't have discussed this on the FL slide, but okay, this is not an argument for FL. It's an argument on how well we can constrain the cross-section, the reduced cross-section, and measure F2, for instance. So the FL has other issues, of course, because we have to maintain this precision for all these points, which we can do. And we can see how well we constrain FL in this slide, if you go here. So I will get to this. So this is an argument that I wanted to make. For the inclusive and for the charm, we don't need to have crazy luminosities. We need to have nice detectors. This is what the point I want to make here. Here is what we do for the charm. Okay, experimentally, and it was shown also by Charles. I remember similar things out of the JLab study. So we need to measure the open charm out of displaced vertex and the chaos decay that we have. So we actually look for a displaced vertex between 0.01 centimeters and 3 centimeters. And this is actually enough. If you see this plot, basically shows the DIS in blue, and among the DIS event, only the charm of decay in red. You can see that as you move from vertex 0, nominal 1 that we consider, to something which is displaced, you actually have only the charm surviving. So this is a very clean measurement, provided that your detector can measure this chaos within this PT range, which is 0.1 to 10, and this pseudo rapidity, which is between -3 and 3. So here we consider this detector, and we have these capabilities. So in the central region, we can measure the chaos momentum between 0.2 and 0.4. Then we have a gap, and then we can measure it in the reach between 2 and 5. In the forward and the rear, we only have reach, and we can measure between 2 and 4. You can translate this to any detector design that you want to consider. Ideally, the more chaos you catch, the more efficiency you have in the measurement. The systematics here. this is the similar totals for the inclusives, also for the charm. You can see the precision of the EIC. And if you take that log factor out, these are still remarkable. And here you can see how much you improve over the theory knowledge. The systematics is 7% we consider here. Now, the systematics, the 1.4 on the luminosity overall, and the electron IET, which we consider 1.6, is the same as for the inclusive. Then you add more systematics on the RHIC and EDP, PID, and on the vertex spine. Now, we can discuss about these numbers. They are very rough, educated guess. But this is a nice goal, because with 7%, we can still do a very good job. So we estimated the background as all the DAS events simulated that pass our selection, but they are not coming from the chart. The Monte Carlo will tell us this. And it's only 1% that passes the selection. So the background contamination is negligible. The efficiency of our cuts are actually around 28. And here you can improve upon if you have carefully designed it. So this is what actually here showed and also what Christian Weiss always shows. So that with the charm, so with any inclusive, you do a remarkable constraint here at lowest. Let's remind one thing here, that here there is no constraint on data. So why we call it EPPS 16 star? We call it star because Hanu, what did actually is to give more freedom to gluons to vary at low ends, not to the quarks, just to the gluons, to have an impact study which is more realistic. Otherwise, the restricting function itself is what is constraining those uncertainties at low x. Otherwise, there is no data constraint. At large x, the charm will do a remarkable job. Here we stop our sensitivity at 0.4. If you want to go to 0.5, you collect more data. So we are assuming 10 inverse retrograde, and if you do, as Charles showed, like 100, then you can get to 0.5. So that will buy you a 0.1 in x at large x.
So come back. This EPPS 16 star looks like the central value is very different from the EPPS 16.
Because it is different.
It's not just the band.
No, it's also the value,
completely
because
changes the.
first you have to reduce the parameters when you fit.
When you release the
And then the
parameter,
central
then the entire fitting function is kind of going different.
Yeah, it goes up. But that's
Because now the central value is almost unity.
But that tells you that we really know nothing on this. This is precisely what tells you.
Lowest shadowing in the 16 and the EPS09, it's an assumption that it's there. This value at the -4, it's fixed.
So 16 star and 16 are probably compatible in RHIC will be.
Oh yeah, of course.
But certainly I I would imagine that the 16 analysis has some of the ultra-peripheral data that is influencing it.
No.
Because the EUPC data is exclusive, they are not using that.
Is this public, this 16 star?
No. I mean,
This is just a feature.
Hanu can provide it, but he only ran it for this. He did a similar analysis for this EC
So when you
impact
make
study.
We did for us and for LHEC.
Yes, and you see the same kind of effect that
We got always beaten up before that because our plots show that we constrain, out to 10 to the -6 or something.
So
Although we have no data there, that really came only from
the argument of those guys at LHEC is that we, in the past, were used to show these same plots down to 10 to -6. And basically, these at certain point go straight. Not here, it is a EPPS 16, but in the previous version, EPPS 09, for instance, we went really straight and constrained nicely. But this is a feature.
Just wondering why the official version is the one that has a shadowing at 0.6 on the central value. This one is not published.
it just gives him wider uncertainty bands and it looks funny.
Yeah, they will train at 1.6 with a band like this, which tells you.
in the way it's published because they have paper.
There are 2 papers, I think.
And then when you compute cross sections, that's usually that.
It does.
Cross sections for P8 actually.
That's right.
It's
It
just
does.
linear factorization prediction. But
That's
in
why
fact,
we always say don't trust your results in this area.
it's all over the place.
In CPGs, if they have statistically motivated accusations, and in this one they just plug in some crazy function. That's why it's not the main person.
That's why we should get crazy for this. We can zero
To
constraint.
figure out what's happening.
If we keep discussing how to constrain something at a little 0.1 more in X because RHIC is something, we miss the point here. But anyway. So, Fn. Here is what we have. Again, this assumes a lower electron energy, this assumes a higher electron energy. In both cases, you can do very nice because the theory doesn't constrain very much Fn for the gold. It's just the point I want to make here that if you compare this performance with HERA in the proton, now we can think about measuring FL for the proton too, and I don't expect very different results in terms of error bars for the proton and for the gold. And so I think that if there is a room where in the free proton EIC can do a huge impact versus HERA is the FL measure. And this is what we now start to consider like assessing. So
Why are all those empirical error bands so tiny? On the right-hand plot. I mean, these are all fits.
yes,
To what? To what data? Yeah, but there's the only proton data in the world.
But they are not fitting that.
They are
It's not
F2,
fitted.
F2,
Yeah.
It's the fit to the whole
F2.
idea. Yes.
yes.
It's F2 and cross sections. They are not fitted.
Proton PDFs are well constrained, and then you can compute them.
I think these are not fitting the data, right, for FL.
No,
so
no,
these are a
no.
computation from the structure function. Yes,
Okay.
from the PDFs. Yes. It's just I was looking more at the error bars and also at the tension between the two experiments, which is unresolved as far as I know. I left those around where this measurement was brewing, and I remember there was endless discussion about the tension between the two. I'm not aware it has been resolved.
They have a combined data set.
Huh?
They have a combined.
For the FL,
I
I don't know.
maybe.
I don't remember.
I don't think they do that. It's not combined.
If you combine these, then it's first you have to solve the controversy. But okay, so this is basically naive argument. So we have room at an EIC to even improve upon the proton knowledge. And also at ElectroWeek that I think PA is starting working on this, and so there is work to do about this. Let me just get quickly to the GPDs and imaging for the nuclei. I'm not an expert on this, and I'm not aware that there has been a huge progress in this field. So it's kind of starting right now to be interesting. So what actually you could do is to use nuclei and do the same as we do for the free proton. You produce mesons or a photon, and here you have actually, there is a nice simulation done by Thomas Lurie and Tobias Stoll back, and again, we are back to the era of the white paper. So when the white paper was crafting, this is the kind of simulation they did. So they simulated a differential cross-section and the JPSI or the phi production, so meson production. You can see here the cross-section, the coherent cross-section with these nice bumps, this is why we call it diffraction, and the uncoherent line here on the top. So you can see immediately that it will be vital if you want to get to the coherent part of the cross-section to suppress the uncoherent, to veto it. And so we think to veto it using a ZDC as a veto for the neutrons coming from the breakup of the nucleus. And this should work very well and suppress the incoherent contribution. Okay, here is a simulation for E-gold, basically, if I remember correctly, Thomas. This is E-gold, right? Mm-hmm. So it's a heavy nucleus. So here we are interested when we do imaging to see where the blue ones are, for instance, and how they saturate if we have access to the saturation scale. So what they did here is the simulation with and without saturation model. So with no saturation is in white, with saturation is in blue. You can see the little sensitivity that you have in the JPSI for the saturation effect, but a nice sensitivity that you expect from the phi. So this will be a golden probe for starting transition into saturation out of imaging on the heavy nuclei, for instance. What about the light nuclei? So we already kind of talked about this when I talked about constraining the flavors of the probe. Well, with the light nuclei, you can do imaging as well, and actually you can study how kind of the nuclear effects set in, because you can span from the deuteron, which is the least dense bound nucleus, to the helium-4, where basically everything starts to look like an aviarium. And the helium-3 is in between, but he's very interested because if you polarize it, the spin actually is dominated by the spin of the neutron. So there are studies about it, also shown at week 1. And so you can study the neutron spin using the helium-3 polarizer. If you polarize the deuterium, you can also study the GPD for different quark flavors. And now, how would you do actually? We think of the technique which is so-called double tagging. So you have basically, you produce a DVCS over an incoherent state of D, so the deuteron breaks, but the DVCS is produced by an interaction with a particle in the neutron, and the proton goes straight. It's detected in the Raman pods, and the neutron is also tagged by the CDC. So both must be tagged, and you have the full exclusive process, which gives you the neutron kind of structure not affected by final state interactions. So this is a very nice tool to do this business. So you can study GPDs of the neutron, and you can study, compare to the proton, the quark flavor separation of UNT, and compare also with what you get from the vector basics. Another way can be also to use helium-3 polarized, and this is experimentally doable, but more complex theoretically, let's say, because here you have one more proton in the name. What is then, to summarize, kind of like the criteria that you expect from a detector to do this game or the imaging? You first need a very good hermetic detector. So you need equal coverage of tracking and calorimetry to a large pseudo-rapidity interval. In ballpark, we consider absolute value of 4.5. And we need, as we discussed, a very good wide coverage T range of the Raman pods that should actually also have a geometrical acceptance close to 100%, which is much better than what we had, which was a few percentage. So we don't want to waste all the statistics that an EIC high luminosity machine will give us, not having the coverage here. For the EA, as I said, it will be vital to have this 0-degree calorimeter with a nice acceptance for the breakup neutron. And here you can see different energies out of a gold ion where the neutron goes in a polar angle and momentum. So if we can cover this, we are fine, and we can suppress the incoherent part. So and also do the double tagging.
So at the NHC EUPCs, you always have this. Like even in coherent diffraction, you always have somewhat one neutron, two neutrons emitted because there's the additional photon exchanges. So do you have those between the outgoing electron and the nucleus?
No, it's at
so it is
1% level or less.
Okay, so this is very clean.
On the other hand, how much can you just pick up photons and make the
In the Raman pods?
No. If in the scattering you have your DVCS on the photon at UT and kick out any neutron.
Yeah. That is for the double tagging, for tagging the DVCS on the neutron.
No, it's just you're trying to do coherent on the nuclei, but you can just kick out the photon.
Yes.
And then your veto with neutron is more or less useless.
Oh, but how much is the
Or you're
Thomas?
putting it in a state that is going to decay much later.
So how much is the possibility that we have a heavy nuclear that breaks up in the incoherent and only the protons are kicked out and not neutrons?
Only protons.
Yeah. How much is the
Oh my
cross-section
God, I
essentially?
think we never.
And I'd say only one proton. If you pick up a surface proton and do a DBCS.
This again comes into this whole.
I think you
I mean, we did studies where we just used evaporation code. There, this is just, you know, I couldn't even find a way not to do that. Now, there's Mark Baker, who works with the Spiegel generator, and he not has evaporation code, but he first starts with an intranuclear cascade. And I think there he sees in the very low excitation range some cases where only protons come out. And photons. So that was his argument that we should have
So
a calorimeter, which has also, should have a photon converter or something from it to detect that. That would help enormously.
So if you go back to a couple more slides, please, where you have the J psi production. So here, that arrow saying suppressed by breakup neutrons, I would say that that arrow only extends down to the peak, not to the dip. Because if you excite the final nucleus to a bound state, that will fill in all those dips. I mean, the cross-section at high T is going to be
I think
comparable
it
to
could be,
elastic.
naively, it could be enough to fit the cross-section also if the dips are filled.
It's actually stunning. You get the Wood-Saxon back already with 2 million.
It's like the claim is from Thomas with this is that you get the whole Wood-Saxon.
It is much better than in EP, because in EP you have this just plain exponentials you're dealing with, but here you have this characteristic diffractive pattern. And I mean, we did it. You just limit the data and then you look like what does 1 minimum give you and so. And it's stunning actually.
I mean, if you already have the max,
gets close, right?
then you can.
I mean, Mark Baker just did the same for JLab energies and finds exactly the same thing.
So if you're, I mean, okay, so you can get the maxima and that will constrain a lot. If you want to get somewhat into the minima, you need a nucleus like lead, where the photons are in the detector are 100 MeV. In gold, the photons that you're trying to detect will be at a few MeV scale, and that's impossible. In terms of facing the background. So you'll never get the deep dips in gold, but you'll get partially with.
Well, sorry, why don't you get them?
Because the photons in the rest frame of the gold nucleus, the photons are 40 kilovolts.
What photons in the rest frame? This is called. This is.
No, the point is that you excite gold to one of its 100 bound states.
Is this coherent?
Well, it's
No, but you don't know it's coherent. That's the problem. By the time you're at
You're
T
talking
equals,
about this low nuclear.
at T equals 0.06, the probability of exciting a bound state in gold is higher than the probability of the elastic transition in that minimum. So near the minimum, your candidate exclusive events are mostly going to be excitations of bound states. So if you want to suppress that, you need to see one of the decay photons. But if most of the decay photons are in the 10 kilovolt range in gold,
No, they're not.
and then you
It's boosted by a factor.
yeah, okay, 10 kilovolts boosted by a factor of 100 is still only 10 MeV, or 1 MeV. And you're going to have a very hard time detecting a 1 MeV photon at 0 degrees. But if you're in lead, the minimum photon energy is 2.5 MeV in every single cascade. So you're going to have 100 MeV photon, and that I think you might have a shot. So
I agree.
So lead it is.
I mean, the question.
But it's
Yeah,
for the saturation, you don't need the full minima, right? But for imaging.
I mean, I'm not saying you should never do gold, but I think lead has some.
Yeah, no. It has some merits. But then we have to really think about putting this photon also calorimeter or
I think
front
we
of
need a
the
very
cell
good
zero.
photon detector in
Yeah,
front of the
that is a good argument.
But that, I think, Mark in his studies has.
And that also solves the placement.
No, you don't. But the question at the end, here you are just saying, oh, we just suppress this. The question is at some point to get realistic and to know how much it's actually going to be suppressed.
So you were there. When you had the short range correlation workshop, there was Mark Baker giving a talk, and he is doing exactly these studies.
Yeah, I know.
With great detail, he's Monte Carloing, goes after Christian Weiss, learning about, every sub effect. This is as realistic at the moment as you can get.
But right now we have no prediction of how much is going to be suppressed in here. I mean, I'm attending a meeting with Mark Baker, so I know what he's
Yeah,
doing.
so, he's trying to figure out how realistic, can be kind of suppressed.
So that's my point. We need to know how much we actually suppress, because
So
here is just a guess.
I mean, the real observable here is the difference between J
Oh, that's
psi
what-
and phi, because there will be no reference curve. I mean, it's very hard to have the reference curve on the phi, because as you change x, the nucleus is changing without any saturation effect. So you don't really know a priori what the non-saturation curve looks like.
No, but you can compare with the phi.
So you can compare phi with J psi. It's the differences.
Correct.
It's the differences between the two.
That's the idea.
That's the idea. That's correct.
But it's good that the chip size is very sensitive.
That's good.
Well,
That's
exactly,
good
that's
because it gives you a
essential.
benchmark. Yeah, it's like
It's essential.
That's
Like a EUPC, you suppress in data. We compare the inputs.
I thought they always claimed they don't see anything.
Well, the suppression can be due to effects other than saturation, shadowing. It's comparable to the effects expected for leading twist shadowing, so it doesn't require any saturation.
all right. But
Running out of time.
yeah, but this is already discussion, right? So, I don't know what we have to discuss. But okay, since I was even asked to talk about RHIC and EUPC, let me just give a couple of considerations. EUPC. So here you have two nuclei that they are interacting from far away by the emission of a quasi-real photon. So this is kind of analog to a photo production in the AS. So we have, in the unpolarized case, some data now, very good data from the LHC, the EUPC. So we have a couple of collections here. I may miss some flavors, but okay, J-Psi, Psi, in lead from Alice and CMS, and also in PLED and in PP. And then we have Upsilon 1, 2, 3S, in PP collisions, UPC. And so we are now counting the LHC number 2's run. So it's like good wealth of data, but what we actually are excited to do at RHIC is that since we have polarization, transverse polarization on the beam, it's the only place before the EIC where you can actually access the gluon GPD, which is what is right now, even in the white paper studies, completely unconstrained. So we would actually like to have at least a pioneering measurement where we have a magnitude of this quantity and realize if it's zero, if it's what kind of size it is, and then we can tune the physics case for the EIC on top. So what we think of doing at STAR is actually to produce J-Psi in UPC and have a transverse polarization, of course, and we already have data on tape from run 17. We collected 350 inverse femtograms at our top energy, which is 510 GeV in the center of mass. We don't have the full acceptance here on the Roman pots, and we think of upgrading this and have a new run around 21, 22, where we consider to collect 700 inverse femtograms. Now, this run can be 22 and 22 because it's actually where, in between, where the beam energy scan program ends, and S-Phoenix is not yet ready to take data, so we have room here to propose a run. So what we did is to use E-Starlight generator to simulate this kind of UPC JPSI, and then account for known star efficiencies and acceptances from other similar measurements. And then we come up with this estimation for yields, which is 28,000 in run 17 and 57,000 signal events in run 21 and 22. This does not yet account to what we actually catch in the Raman pods, because here we have one proton which is diffractive, goes straight, and so this is a diffractive proton that we have to measure and tag in Raman pods to have a good measure. So main detector has already a good coverage for these 2 decay electrons from the JPSI. So this is the pseudo rapidity of the 2 electron, and here you can see in the black dashed line what we cover at star currently, which is basically around what we have the maximum production here in the barrel. If we have a forward upgrade that many of you may be aware we are proposing, then we have an extended coverage here at larger forward rapidities, and this is the purple line. It could be nice, but in this program it is not vital at all. What is actually more vital is to have a better spectrometer, a better Raman pods. Because what we have right now are only 2 stations like this, one from the top, one from the bottom, square shape with a dead area in the edge. And we don't have room to put lateral stations. So what we envision now is a geometry like this. So we put something which goes on an L shape. Possibly if we have curved edgeless sensor, they can go even around the profile and go from the top and the bottom, they can close up to make a full phi acceptance of the Raman pods. So we estimate the increase in our acceptance after this proposed upgrade, and it could increase our factor 2. So this is a significant increase for this time. This is a microstrip, silicon microstrip. So what we think is either to have edgeless silicon microstrips or just a microstrip that we use now, but on one superimposed to the other to do an L, and another L on the other side, and then we put some little horizontal motion to close up. So this is not a complicated upgrade to us, and we are thinking of realizing this if we have this run in 2021. So
how well can you predict a priori how close you can get to the beam?
We have the beta star of the beam, and you have to stay 10 sigma away, right?
And so you can just take that number on the chalkboard and say, once the machine people are done tuning the beam, I can reel it in, and
that's what we do, right?
And so that's
they just say, they call us in the control room and say, like, we are ready to put the Raman pod. And we have past experience on what you actually lose in average of every run, like this first 5 minutes, and so on, that is accounted in the estimate.
But so you don't sometimes find you need to go to 15 sigma, and other times you go over to 8 sigma.
No, it's pretty standard, because then it's operated by the crew in the shift, so they will not have freedom to decide how they want to go 15.
No, but the beam might have the freedom to have more background, a bigger halo in one run than
and
another.
cause problem, so the machine people should tell you, don't do the wrong pods because we have unstable conditions, But in the first days, usually there is some expert sitting there and evaluating case by case, but once you are over this shift crew, then you cannot tell them, every run, look at the ground, put 15, 14, 13.
But okay, so you don't, but
It's already safe to put around 10, and then you can evaluate day by day and maybe vary.
What's 10 sigma in great distance?
I don't know.
I don't know, is it
It depends on how
5
wide
millimeter,
it
is it millimeter?
It's certainly
No.
It's fine at all.
Yeah. It's fractional centimeter.
It's a millimeter.
Yeah, I would say.
Yes.
It's not micrometer, it's not meter.
It's not centimeter. Okay, so we actually start to talk about Wigner now. So this is another thing which is not mentioned in the paper. In the white paper is mentioned the Wigner function. Of course, we say that we integrate over it on KT or BT and get to the TNDs and the GPDs. We also say that is a 5-dimensional quantity that I like to call the genetic, the DNA of a proton, because it contains all the information. But in the white paper also we state is something that there is no idea things evolved in this field, and we are lucky that now there are processes proposed to constrain this. One was, I remember I was there at the EIS in Birmingham. It was proposed by the student of Andreas Metz. In UPC, you can have double Drell-Yan process, and this could constrain Wigner and Quark's Wigner. This is nice academically, but I don't come up in my mind any facility now or in the near future that can measure double Drell-Yan successfully, because the cross section is very, very low, to the level or below the one of the double DCS. So another project proposal from Yoshitaka Hata, Bowen, and Fan is to measure the gluon Wigner in diffractive dijet production. So you can do this in EP. Actually, they first proposed in EP for LHIC and EIC, and then they 1 year later they also updated it and proposed for the UPC. This can be a very nice constraint at the EIC, and if we can do it UPC at RHIC or LHC, it can be a very nice pioneering measure. So in UPC, what you need here is to have unpolarized. Here we don't polarize anything, or at least we don't consider polarization. Proton-proton or PA collisions, where here the one proton or A is the photon source and the other proton is the diffractive scattering. So we have a veto of proton or nucleus breakup in the Roman post of the EUPC. We have the exclusive requirement, exclusivity, and use a Roman post to then measure the other proton, which is the scattering. The same as for the JPSI basically. So LHC is also investigating this possibility. The problem is that this process has very low PT jets. Here we are talking of jets of the order of 4, 5, 6, up to 10 GeV in PT. LHC has very good accuracy for jets above 50. So at STAR, on the other hand, we are in a sweet spot because we have a large acceptance detector for low PT jets, and we have proof of concept papers already that measure the jet. Plus, we have the Roman post, as I showed before, to target the diffractive proton. And if we upgrade, then we will have even better spectrometer. So this is what we want to do now, and actually we estimated a yield of 8,000 events in proton-proton collision at our top energy, using this, assuming that we will have this future run of 700 Sventobar, and also assuming that we have the upgrade that will buy a factor 2 in acceptance. So assuming all of these caveats, we may have around this number of events, which give already has the capability for a pioneering measurement at least, and then the EIC will be what constrains even further the gluon Wigner. So everything here, and what I showed also for the JPSI estimates, is actually what I did personally in a couple of months. So it can be done an even better study and ensure that people pick it up now. For a failed grant proposal for the theory of the career award, so it didn't go through. But this is kind of a base now for hopefully for people to think about this and realize this program, which is, I think, very crucial for the EIC. So,
sorry, just quickly to come back to that. I mean, from a theoretical point of view, there's no actual restriction on PT of the jets, right? The only thing you require is that the dijet system was launched in their mass. But you
And low net
anything
PT.
about
The net PT has to be small, but the PT of the individual jets.
I think that is the actual simulation that shows that those PT are small. It's not a requirement for
This cross section, of course, crazy.
Yeah.
Dies like crazy when
Yeah.
you go to large.
Exactly. So it's just a feature of the conception.
But how well do you have to know the
But-
PT of the jets, of the individual jets, in order to do the Wigner analysis?
Well, that's a good question. That's what actually has to be assessed if you want to do this at the LHC. I don't know the answer. I think that, for instance, Yoshitaka is working on this right now, on kind of getting the feelings of what is the precision you want to achieve in the PT of the jet. That's a good question.
Those jets could be also heavy cloud jets, right?
no, you would have different, well, you would have additional Wigner distributions. If you want only one, you need mass restriction.
would be also interesting.
Well, you have at least as many bigger functions as you have GPDs and TMDs, so
Exactly. So
it must be
infinite number.
55.
Another stamp collections. All right, so, but again, the field is evolving, it's a good thing. So this is also the point of observation in summer. We had old studies on, so the white paper era on DVCS and how we constrain GPDs out of just the DVCS measurements at an EIC. And this is nice studies, but we cannot just rest now on our laurels. We have to go back to the board and have new studies performed, and this is what we did, for instance, for the nuclear PDFs. Both the DNL and the JLab communities are focused on how we can constrain the PDFs. This is already something beyond what we show in the white paper. So in an updated version of the white paper, I'm sure that we can do strong arguments on nuclear PDFs. And new excitement is ahead. So we need to complete all these PDF studies, and we have a community now re-engaged somehow, because it was slowly dying, the TPD community. Now it's re-engaged around the problematics of adding the methods. Also, full fits are the next really goal. This is a challenge, and we want to complete this and get ready for the EIC to come. And the nuclear GPDs, as we discussed now, is something that starts to be under the radar, let's say. Wigner function, it's another milestone that was not in white paper, and I think it should get in as we perform more studies and get to feeling about this.
So, what is there on nuclear GPDs? Is there any?
There are some calculations.
There are some calculations.
There is one measurement on helium-4 at JLab with fairly large.
The only data I'm aware of from JLab.
Yeah, there will be new measurements, higher precision, higher Q-squared measurements from JLab.
There are some points for them, it's but they can give about it's almost like
I hope we will get some coherent deuterium data. Well, maybe from
So Hermes says this.
maybe
For heavy nuclei.
even for light nuclei, they are over.
Yeah, exactly. So
Question is, do you want nuclear GPDs at all?
yes.
What you do? That was last week.
I mean, what,
Why you don't want a G?
Well, you can learn about how the gluons are distributed without going through the whole GPD apparatus.
well, there's quite.
That actually is sparking controversy.
That's a very good.
Yeah. If you can actually claim that you can see the gluons out of just the Fourier transform, right?
That's the idea.
So if you talk with Andreas Metz, he's not.
What does he think you see?
But even flavor, I mean, decades ago, people were extremely interested in understanding the difference between proton and neutron densities in not Z nuclei. That's motivation for the P-RAD